and welcome to our first lesson on this YouTube channel. Today we're going to talk about machine level representation of data. This of course will be split in multiple subchapters, with the first subchapter called number systems. Now you may be wondering, what are number systems? Well, by number systems we mean stuff such as binary, octal, of course, decimal, and finally hexadecimal. Think of them as languages that computers can understand, with binary being English and hexadecimal being something less known but still pretty known, such as French. Understanding these number systems will help us understand better how computers think and the way they analyze things. Now we will go one by one and explain what each one means. So we're going to start with A, binary. Binary is represented by 0 and 1s. For example, 0, 1, 0 is a binary number. But for it to actually be written as a binary number, we have to put this underscore 2. This subscript 2. This subscript 2 represents that it is binary. As you can see, binary can only be formed out of two numbers. Because bi means, guess what? 2. Now, the next one, B, is gonna be the one we started, the second one, octal. Octal is numbers 0, 1, 2 to 7. For example, a number in octal would be 217. Of course, for it to be written in octal, same as in binary, you have to put this subscript 8 here to show that it is actually written in octal. So, this is octal. As you probably figure it out, octal means 8. Why? Because here we have 1, 2, 3, 4, 5, 6, 7, and 8 numbers. Because from 0 to 7 we're going to have, of course, 8 numbers. So yeah, this is octal. So I understand we have this octal and this binary. So for example, 0 in binary is going to be 0, 0, 0, 0. You may know, but for people that may not know this, 1 is 0, 0, 1. I'm going to explain later why actually this is true. But for now, just know this is how it looks like. 4 is 1, 0, 0. 5 is 1, 0, 1. 6 is 1, 1, 0. And 7 is 1, 1, 1. So this is how we write octal numbers in binary. Now C. C is gonna be our decimal. How do we write decimal? Well, decimal is of 0, 1, 2 to 9. Because guess what? 9 numbers are from 0 to 9. And deca means 10. For example, decimal number would be 297. And of course, as we did for binary octal, to represent it and show it is decimal, we have to put this subscript 10 here. So 297, 10. Okay. And now the last one, also known as D, is hexadecimal, which is written as 0, 1, 2 to 9. But you may be thinking, but we need 16 numbers, right? Because we are talking about hexadecimal. So we have 10, which is going to be written as A, 11 as B, 12 as C, D, 13 as D, 14 as E, and 15 as F. So I understand. A means the number 10, B means the number 11, C means the number 12, D means the number 13, E means the number 14, and F means the number 15. Now, there are two ways of writing hexadecimal numbers. The more conventional way and the less conventional way. The less conventional way would be to write it like this. Let's say we have the number A0B8. And of course, as we did for binary, decimal, and octal, we're going to write subscript 16. This is less conventional. Now, the more conventional way is to write 0xa0b8. This is the actual conventional way to write it. Okay. Now, as we did for octal, we could also represent all hexadecimal numbers as binary. For example, 0 is just 0, 0, 0, 0. 1 is 0, 0, 0, 1. 2 is 0, 0, 1, 0. Again, as I said for octal, you'll understand later why is that. But for now, just accept it as it is. With an explanation coming in the next lesson on why it is like that and not somehow else. 9 is 1001. A is gonna be 1010. B is gonna be 1011. C is gonna be 1100. D is gonna be 1101. E is gonna be 1110, and F is gonna be 1111. So this is how we represent hexadecimal numbers in binary. Okay, now that we know that, I will want also in this lesson to explain a bit of some conversion algorithms. And the first one we're going to talk about is anything to decimal. So any number to decimal. Let's start first with A, with binary to decimal. What is this? For example, let's take the binary number 0012. How do we find its decimal equivalent? Well, we first look at the number of bits it has. 1, 2, 3. It has 3 bits. So, how does this help us? Well, to translate it to decimal, we're going to use the following. We're going to say 0 times. And we're going to look, okay, so we have 3 bits. So we always start at the power of 2 and minus 1. So in our case, 2, 3 minus 1 is going to be 2 at the power of 2. Then it's a sum. Then we think, okay, so now we are at the second bit. So if we go by its logic, now it's going to be 2 minus 1. So it's going to be 1 times 2 at the power of 1. And it's going to be 1 minus 1. When we are at the last bit, it's going to be 1 minus 1, which is 1 or 2 at the power of 0. Sort of, it goes descendant from the number of bits, starting from the n minus 1. So if you have 3 bits, you start with 2 at the power of 2. If you have 8 bits, you're going to start with 2 at the power of 7, 2 at the power of 6, 2 at the power of 5, 2 at the power of 4. Always remember you're going to stop at 2 at the power of 0. No matter what, you have to stop at 2 power of 0. So look at the number of bits and do the number of bits minus 1. And this is going to be the first power you start with. Now, as we know, 0 times 2 at the power of 2 is 0. 1 times 2 at the power of 1, 2 at the power of 1 is 2, so it's going to be 2. And then 1 times 2 at the power of 0 is going to be 1. So in decimal, this is 310. That's all. Now let's get a bigger one. 1, 0, 1, 0, 1, 1, 1, 0, 2. Now let's count the number of bits it has. 1, 2, 3, 4, 5, 6, 7, 8. What does this mean? This means the biggest power it can have is 2 at the power of 7. So we take one by one. So we take this one. It's going to be 1 times 2 at the power of 7. Then we take the next number, is 0. So it's going to be 0 times 2 at the power of 6. Then we take the third number. It's going to be 1 times 2 at the power of 5. And then the fourth, 0 times 2 at the power of 4. And then the fifth, 1 times 2 at the power of 3. The sixth, 1 times 2 at the power of 2. The seventh, 1 times 2 at the power of 1. And of course the last one, the eighth, 0 times 2 at the power of 0. This is going to be equal to 1 times 2 at the power of 7 is going to be 1 times 128, so it's going to be 128. Plus 0 times 2 at the power of 6 is 0. Plus 1 times 2 at the power of 5, it's going to be 2 at the power of 5 is 32, so it's going to be 1 times 32 is going to be 32. Plus 0, it's going to be 0. 2 at the power of 3 is 8, 1 times 8 is 8. 2 at the power of 2 is 4, 1 times 4 is 4. And, okay, 1 times 2 at the power of 1 is 2. And 0 times 2 at the power of 0 is 0. So this is going to be equal to, when we sum them all together, 17410. And this is the decimal equivalent of this binary number. Now, we will talk about binary 2 octal to decimal. So how do we do octal to decimal? Well, let's take an example. 5768. Now here it changed. The logic is still the same. Count the number of bits, 3. And then, of course, it's going to be n minus 1 power is going to be the first power, the largest power. The only difference is this time you're going to do, so let's take the 5. 5 times, but being octal base 8 is going to be 8 at the power of n minus 1, the first one. So in our case we have 3 bits, so it's going to be 3 minus 1 is going to be 2. Plus 7 times the second one, 8 at the power of 1, because now we're going downward. And again, like previously, at the third number, at the last number we always end at 8 at something at the power of 0. In binary it's 2 at the power of 0, in octal it's 8 at the power of 0. In this case, this will give us 5 times 64, which is 320, plus 7 times 8, which is 56, plus 6 times 1, because 8 to the power of 0 is 1, which is 6, which in decimal is going to be equal to 382.10. Now let's take another example. 37618. This one, as you can see, has 1, 2, 3, 4. Has 4 bits. So the largest power is going to be 8 at the power of 3. Let's check the first number. 3 times 8 at the power of 3 is going to be the first number. Then we go down to 7 times 8 at the power of 2. Then the third number is going to be 6 times 8 to the power of 1, because we're going down with the power until we get to 8 to the power of 0. And the last one is 1 times 8 at the power of 0, which is going to be equal to 3 times 8 at the power of 3 is going to be equal to 1536, plus 7 times 64 is going to be equal to 448, plus 6 times 8 is going to be 48, plus 1 times 1 is going to be 1. This is going to be equal to 2033, 10. This is our octal to decimal. And for the end of this lesson, we're going to do our last one, which is C, which is going to be the hexadecimal to decimal. And this goes with the same logic. So let's take our first 0x32a. So we first count the number of bits, aka everything that's after the x. 1, 2, 3. So we have 3 bits. So what's the largest power? Something at n minus 1. As we know, hexadecimal is 16, so it's going to be, our largest power is going to be 16 at the power of n minus 1, and the last term will have 16 at the power of 0. So we take 3 firstly. It's going to be 3 times 16 at the power of n minus 1, so 2. Then our second term is going to be 2 times 16 at the power of 1. And our third term is going to be a. We know a is 10, so we're going to write it as 10 times 16 at the power of 0. Which this is going to be equal to 768 plus 32 plus 10. Which is going to be equal in decimal to 1, 10, 10. You see? Pretty easy. Now, let's do another example. 0x0abf. We read the number of bits we have. 1, 2, 3, 4. We have 4 bits. So our largest power is going to be 16 at the power of 4 minus 1, 16 at the power of 3. And we must end at 16 at the power of 0. So we're going to have here 0 times 16 at the power of 3 plus a, we know is 10, so it's going to be 10 times 16 at the power of 2. Then we have b. B is going to be 11, because we know b is 11. 11 times 16 at the power of 1. And then we know f is 15, so it's going to be 15 times 16 at the power of 0. This is going to be equal to 0 plus 2560 plus 176 plus 15, which is going to be equal to 275110. So yeah, to convert anything to decimal, you just count the number of bits and then you go with the something. So if you have binary 2, if you have octal 8, if you have hexadecimal 16, at the power of n minus 1, with n being the number of bits, and then you go down until you reach